Hello everyone. So this is our second meeting for the case 2018, and our topic today for discussion is the pipeline. And what we're going to talk about today is not going to get into super details, and we are only going to focus on standard and traditional pipeline structure for a machine learning algorithm. So let's jump into some overview of the topic today. So if we want to put it even more brief, we're going to talk about like how the entire structure kind of looks like. You can see from the first line of three phrases. The first thing is how we prepare input data, and the second step is just to process this input data with some kind of models. And the third thing to do, and the final thing to do, is to make predictions for the output data. And to go into a little bit further details, there are mostly 5 steps or 4 major steps. And the first step is just to prepare data, and then we extract some features from those data, and we train these data with machine learning models, and then we make predictions. And the fifth step is usually optional, and is especially important for those people who are trying to present their work to other people through research paper, through presentations. And the fifth step is called visualization. So let's get into how we prepare the data set. So to take, for example, I screenshot a previous paper that I worked on the left-hand side like this, and we're gonna just subtract some words or phrases out of this paragraph to see kind of how preparing data looks like. The 3 phrases or 3 quotes that we extract are listed here. So the first one is dataset is examined. The second one is continuous variables, and the third one is the following attributes are binary. Let's look into how this means and how these can help us understand what preparing data means. So the first phrase, dataset is examined. Examine if the dataset is healthy and complete is our goal in this process. So basically, first of all, we will organize the dataset into some kind of readable document for the machine learning algorithm to read in the future. So usually, the platform that I like to use the most is called Jupyter Notebook, and we usually just program with Python on a Jupyter Notebook. And in that process, we can just type in some algorithm to read the documents from our local computer. And usually we will organize data into arrays, rows and columns into .txt file. And in this process, after we organize the data into a readable document, we'll examine if there are any missing data and if there's any lost data points. And this is especially important because it basically tells which features are healthy and strong for our analysis, and we can focus on those features for our future training. And also for those features that are has a huge problem with their data set, we usually would try to use some methods to process it and to either eliminate it or make it more healthier. And the second quote says continuous variables, and the third quote says the following attributes are binary. This basically means that we are examining the data set to see what kind of data are contained in there, and this helps us to understand which kind of methods or machine learning training models are best for our method to be trained. So the first question to ask is always what kind of variables or what kind of numbers are in there. So basically, there are following 4 categories of input data set. The first thing is continuous number, such as temperature and housing prices. These are continuous numbers. And to train these numbers, we usually use regression models. And the second kind of variable is called discrete numbers, such as what is the weather tomorrow? It's either going to be sunny, rainy, cloudy, or gloomy, or those kind of stuff. So it's binary. The reason why it's binary is because they usually have like or say this is discrete. The reason why it's discrete is because there are discrete numbers describe each situation. There is like 1 stands for sunny, 2 stands for cloudy, 3 stands for rainy, and there's no number in between. So it's either going to be 1, 2, 3 or some other numbers. It's not going to be a continuous number in between. So for these kind of problems, we're usually doing is to find a classification for these categories and to divide them accurately and to predict the weather, for example, for tomorrow or for entire next month. And the third kind of data is just the data with a bunch of features and without labels. for example, for the two previous categories of numbers, they all have labels. Like, for example, my x-axis can be the number of days, and the y-axis can be the label for the continuous number. We can say the housing price for each day, and the discrete number I can say the number stands for the weather of the specific day of the number of the days. But for this, we don't have a label. We only have some kind of features for a given sample point. So what we're doing with this is simply put is some kind of unsupervised learning, which means that we don't try to use a model to correlate the input data variable with a specific label output. And what we're doing here are usually kind of clustering. Like we are grouping some data points of certain kinds into one group and some into other group. And one example of this kind of training are some product recommendation from restaurants in Amazon. Like if you buy certain kind of books, the most they will tend to use their algorithm to predict what kind of books that you like and to recommend specific category of books to you specifically. And the fourth kind of is just to predict the optimized movement. And this is done by the machine going through all kinds of possibilities of the next movement and to maximize the words for each movement so that way it can get to the best move for the next step. And one example for these are the AlphaGo that we heard about from Google. They just play Go's with human players and it just retrain itself each round so that way it gets the best outcome. And the thing for this process is just like there are a lot of applications for game playing and even for self-driving cars. So these are the four major categories that we're trying to train with, and as you can see, there are like very different number inputs. So to prepare the data, which we mean to examine each data point to see what kind of data it is and to see what kind of training problem it actually is, and we can translate them into the four categories that we just mentioned. And with these, we can try to determine what kind of machine learning algorithms are the best for them to be used. And the second step is called feature extraction. Why we need a feature extraction? So basically, the major problem that we're probably going to deal with in the future is called the crystal dimensionality. And the thing for this is that usually the two major numbers that we consider for a data set is sample size and the feature size. For example, for the data that we have for my previous machine learning project, which is presented like we got a paragraph like 2 slides ago. It is the pre-processing step of the entire project, and in that project, the data set we got was pretty bad actually. So because we only have 272 breast cancer patients, which means we only have 272 data sample points, or the sample size is only that small. But we have 1,567 attributes, which means we have 1,500-ish features. So we have much more features compared to the sample size, and this is not good for our training purpose. So this is called cursor dimensionality when we have more feature numbers compared to the sample size. And usually what we're trying to do is to keep the feature number down to either be equal to or smaller than the sample size. And this is definitely not good for our training purpose. So what we're trying to do is called the feature extraction. Just kind of, to put it simply, we're just trying to eliminate some not so significant attributes and to leave only 272 or less significant attributes for the prediction purpose. And we can actually talk about a little about the methods for the feature extraction. And in the future, we're going to talk about more into details of each of the models or the methods that we use to select the features. But here we're just going to put it simple. And these methods usually based on just they're kind of just different ways to rank how helpful each feature can be for us to train our model. So that way, according to their ranking, they can select the top whatever number of features for the feature training. So for example, there are PCA, principal component analysis, stepwise selection, feature correlation, and stuff. So, for example, the simplest is everyone knows that they are like R squared scores. So like it just like shows how strong the correlation between the feature and the result that we're gonna predict, how strong the relationship is. So basically, we just list the R squared score for each of the features, and we select the top the top features with the top R squared scores. And this is one of the ways. And it's like for stepwise selection, we just trying to do similar stuff with another kind of equation to rank each feature with a certain score, and we're going to select the top scorers from the whatever number of attributes we have. And also another thing to mention is that aside from cursive dimensionality, there are also other situations that we're going to be able to use the feature selection too. For example, if we have too much attributes and actually we have a lot of sample size, so we don't have to worry about the cursive dimensionality. But like the computation time is still very time consuming and resource consuming. So usually what we're trying to do is always to keep the feature number down so that we can reduce the number of training time, and that can be really helpful in the future when we are actually dealing with a very large data sample. And basically, so feature selection is also useful for saving computation power or to reduce the computation complexity. And the third step is just to simply train the model. And here is where the traditional machine learning ideas or deep learning kicks in. Actually, I think you guys might have heard of machine learning and deep learning a lot from those experts or news, whatever TV show or blogs, and they're nothing that special. So basically, they're trying to deal with 4 categories of problems only, and like for regression problems, we have linear regression, XGBoost, support vector regression and stuff. And for classification, we have the simplest and the most traditional logistic regression, and then we have decision tree, random forest, and support vector machine. And for the third category, we have, which is unsupervised learning. Basically, we're doing clustering. To put it into English, we are doing categorization methods such as similar item recommendation stuff. And the fourth category, we just talking about reinforcement learning, such as robot movement and gaming design stuff. And the process are just, we usually select the model and set training step and train to reduce the loss function that we define, and then we produce the result. And this is the simple process of the model training. One important thing in this process is how we define the loss function. And the most recommended and the prominent loss function is called the reduced mean squared error. And this is it's not defined by the equation here. In case that you guys haven't taken AP statistics or anything related to statistics already, we can talk about how this equation basically means. So in this example of a linear regression model, we fit a line for a line here, a straight line here, for the data point represented here. So what linear regression means is just like you have a bunch of data points here, and you're trying to fit a line to show the trend of these data points and to generalize it into a straight line. As you can see, this line doesn't necessarily have to go through any of the points in this whole data set. It only shows the general trend of the entire data set of the points. So, of course, there are a large difference between this line, which is the predicted number, compared to the real number extracted in the study or in any experiment. And this difference is shown by by the distance between the predicted number and the real number. So what we're trying to do with reduced mean squared error is just to square all these values, all these distance, and then we add all these squares together, then we divide it by the total number of sample size, which is just kind of to take the average of all of them. And then we get the mean squared error. This idea is very straightforward but powerful. In the future, like if we're not only discussing about a straight line, like we're fitting a really complex function, we can still calculate the mean squared error. And by reducing the mean squared error, we're trying to reduce the distance between the predicted value and the real value in general. And then we can reduce, we can reduce the prediction mistakes or prediction errors, and to increase the prediction accuracy. Finally, we're talking about a prediction now. So for prediction, there are again 4 categories of counter predictions, and now we're going to focus on the simpler ones, which are supervised learning predictions, which includes classification and regression. For example, the first figure shows a very famous example, which is called MNIST for deep learning training. In this case, deep learning is trying to, you see, we have a training data set, and we have a training label, which means it has labels, which means it's a supervised learning. And then we're trying to correlate this number, this figure, to this label. And in this case, although we're using deep learning instead of machine learning, it's still a regression problem because we're just trying to correlate these 2 figures. Oh, actually, this is a classification problem. We're trying to classify each picture into 10 categories, which are from 0 to 9. So we're classifying these pictures, basically. And for this one, this is also a screenshot from the project that I worked on before, which is the same project as it is in the previous sections. And for this one, we're just trying to extract significant genes for each category of the things that we're trying to looking for. And this again is also a classification problem. And for these results, what we're trying to predict are just the relationship between, for example, for the first one on the left, we're trying to predict the relationship between the figure and the labels. And usually we have a training data set like this, which has the pictures that we're trying to identify or to train with. And we also have a label to see how this picture actually is. And after the training data, we have the testing data to be tested without label, and we only have the image input for the model to again identify what label it can be. And also we have a set of labels for those testing data points to see what it actually should be, and then we can get the error of the prediction. In this case, after the entire training in the future, we will only have the pictures input after the training, and we'll have the machine to judge what label it should give. And usually the prediction accuracy is really high, and currently the highest can be achieved at 99%, which means if I give a random hit-random number, and it can for the 99% of times to predict correctly of what that number actually is with the labels assigned. And finally is the visualization. So basically what we're trying to visualize are the process of us preparing data, and also the process of training the models. So basically, we usually use a lot of different kinds of graphs. It's totally up to you to decide which which graph or which kind of figure is the most useful for your training purpose. And for example, for us to show our data set, or to show how our data set actually distribute, we use this color-coded map, or say the heat map, to show the distribution of our sample data point. And in this case, the more mixed of the 3 colors, which are red, yellow, green, the more mixed they are, the better the the data set is. And the second thing are just to show the entire process of the model training and the result. And here is one of the results that we have in our study. And in this graph, basically what it says is the closer these 3 lines are to the top left, the better the training accuracy, or the better the training process is. And as you can see, all these 4 cases, they have pretty strong trend toward the top left. And to show how our model actually works, I want to present to you this thing here. Sorry, just a second. As you can see, these are all the graphs of the methods that we used. So for the model training purpose, here this is the tree graph of the decision tree that we used, and this is the graph of the random forest that we used. And we also visualize the random forest like this. And visualize the PCA process, which is the feature selection process that we use to select the data. So visualization, in short, is just a process that you will usually use to visualize the data that you use, and visualize the training model and the training process that you have gone through with your project or with your machine learning methods. And this is it for this meeting. So to, again, bring back to the overview, we have these 5 processes for the entire machine learning pipeline. And with all these, we can just start to make predictions with machine learning and deep learning. And in the future, we're gonna specifically talk more about each different specific methods on feature extraction and model training. And finally, before we're gonna jump into personal project for the club members, we're gonna talk about visualization too. Thanks.